PhD candidate from Binghamton University. Today I'm going to be presenting my paper titled Deep Compress VIT Rethinking Model Compression to Enhance Efficiency of Vision Transformers at the Edge, which is accepted for publication at CVPR 2025. Deployment of VITs on edge devices presents significant challenges due to their substantial memory requirements. For example, Vision Transformer Small requires 84 MB. This requirement often exceeds the on-chip memory limit in edge devices. The on-chip memory limit in edge devices is typically 1 to 8 MB, so the model parameters must be stored in off-chip memory, requiring a sequential processing approach during inference. This involves iteratively loading each layer's weights into on-chip memory and performing computations on that layer before proceeding to the next. This process introduces significant latency and increased energy consumption due to frequent off-chip memory access. So what can be a possible solution to this problem? A possible solution is to adopt model compression to compress the model parameters to occupy less memory. So the existing compression techniques can be broadly classified into two types. One is pruning and another is quantization. With pruning, we can see that we can achieve a moderate compression ratio, but this results in significant accuracy degradation. Whereas in quantization, we achieve a large compression ratio, but still it suffers from considerable accuracy degradation. Whereas our objective is to achieve high compression ratio with low or minimal accuracy degradation. So what is the bottleneck in existing model compression? Existing model compression, pruning, and quantization both perform some sort of weight encoding, but they lack a decoding step. This is where deep compress VIT comes. Our deep compress VIT designs an encoder to encode the weights to occupy less memory, and we also have a decoding step utilizing a decoder to recover the accuracy degradation. So we can achieve a high compression ratio with low accuracy degradation. So deep compress VIT performs unified compression training to achieve this high compression ratio. The encoder and decoder for encoding and decoding the weights are jointly trained with the vision transformer model to achieve minimal performance degradation or high task performance. One thing to notice is that the weight decoding in deep compress VIT leads to inefficiency in terms of flop count, because the flop count increases because of this weight decoding that is carried out each time during inference is done. To prevent this, we design a lightweight decoder using a single fully connected layer, which makes the overall computation graph a series of matrix multiplications, and we leverage the associative property of matrix multiplication to optimize this weight decoding, and we call this optimized test time decoding, which prevents any flop count increase during inference, and our overall flop count becomes less than or equal to the original flop count during inference. As can be seen from the graph, our deep compress VIT achieves a 15 times compression ratio with less than 1% accuracy degradation. In comparison to other existing compression techniques, our deep compress VIT achieves remarkable compression ratio with high performance. In summary, deployment of vision transformers on edge devices presents significant challenges requiring frequent off-chip memory for loading weights, and existing compression techniques are ineffective to compress VITs to store the entire model weights on on-chip memory, particularly because of large accuracy drop at high compression ratio. To address this issue in this work, we propose an orthogonal compression technique that involves encoding and efficient weight decoding at runtime to achieve high compression ratio with minimal performance degradation. Finally, I would like to thank our collaborators for their significant contribution in this work. Thank you for listening to the presentation.